Assalamualaikum warahmatullahi wabarakatuh. Good morning. Today we will continue our chapter discussion about the special type of CRO2. Okay. The first one we will talk about the storage oscilloscope. As you can read in our textbook that storage CRO can continue to display waveform if we didn't connect the input. So if we use the conventional CRO, so if the input signal is disconnected from the input port, so we cannot display the signal or the waveform signal in our oscilloscope. So in this storage oscilloscope, this kind of type of oscilloscope, we can save or we can display the waveform image after we disconnect the input signal from the input oscilloscope. And the duration to display that kind of waveform after the input signal is disconnected from the input port is depending on the kind of the oscilloscope, and the variation is about the few seconds to several hours. So two popular technique in oscilloscope CRT is the first one is the mesh storage, and then the second is phosphor storage. We can see in this block circuit from the mesh storage circuits, the mesh storage CRT is content of dielectrics deposits on a storage mesh, and a collector mesh, a float guns. This is a float guns, collimator, collimating electrolyte, and the additions to the elements of the standard CRT. So it's like writing gun, horizontal deflecting plates. This is the common in conventional CRT, and also the display. The display, or in this case, is phosphor screen. You can see here. This is the phosphor screen to display the waveform. And another kind of the oscilloscope is phosphor storage, and this is the target structure of the phosphor storage CRT, and we will talk about this phosphor storage later. So the characteristic of the mesh storage CRT you can see in figure 5.10 and also 5.11. In figure 5.10, common or the most material when bombarded by the electron have a sufficient energy, and we have the bit between the first and second crossover. You can see this is the first crossover, and then we have the second crossover. The more electrons are emitted then that are absorbed by the material, and a net positive charge is the result. You can see we have a two first crossover here. This is the first one, and then the second one, and between the first and the second, the more electron will be emitted, so we got and absorbed by the material, so we have a net positive charge. And we can see before the first crossover, a net negative charge with results, and the electron don't have a sufficient energy, so there is like a very small electron can be emitted to the material. So we can see this is the secondary emissions, and then this is a storage mass potential here in figure 5.11. So before the first crossover, the collector mass voltage is around 45, 0 to 45, and after the stable conditions, after the first crossover, we can increase the voltage of the collector mass until VC. VC is cut, this one, the VC. And this representation of the secondary emission we can see here. In this situation, in this area, the more electron will be emitted to the material. It can that we can increase the collector mass in the this is the collector mesh, this one. So if the electron emit to the material, there's a more carrier through the material. It means that we can increase the voltage of the collector mesh. So you can see here, this is the storage mass potential. And this is the condition. So in order to store waveform, we can assume that the storage surface is uniformly charged to the lower stable point, and then the right gun is biased well beyond the first crossover with respect to the storage mass potential. So you can see in the textbook that in figure 5.12, where the secondary emission ratio here, is much greater than unity, so this area, the storage surface hit by deflecting beam, will lose the electrons. So it will be collected either by the collector mesh or display phosphor target. So if we can increase the electron volt of the electron, I mean that between the first crossover and second crossover, we can increase the collector mass. So we can store the waveform and display in the phosphor target, like in this one. So in the phosphor skin, we can store here the electron and then to display the waveform and then display in the phosphor screen. So it's between the first crossover and second crossover. And for the phosphor storage, Robert Anderson developed the bistable phosphor storage by using similar principle of secondary emissions. So if this one, we use the secondary emission ratio in the mesh storage, and in the phosphor they use the similar principle. Okay, and these two approach, I mean that this phosphor storage and mesh storage is the comprise the commercial storage CRT construction today. So we can see here this in the bistable storage tube, the same material is used for both the storage target and the display. The material used is a P1 phosphor doped for good secondary emission characteristic. So basically the phosphor storage and also the mesh storage is similar principle and also similar block circuits. But in this phosphor storage, the storage mesh here we replace by using the material like a P1 phosphor. So you can see, so the similar material, if the storage mass in phosphor screen in this in the first kind of the storage oscilloscope is we have a different material, but in phosphor storage they use a similar material. Okay, similar material for the storage target and also the display. Okay, and A necessary condition for such a target is that boundary migrations of stores charts must be eliminated. So in this kind, the only differences between the storage mesh and phosphor storage is the material for the storage mesh. Okay, then the controlling electrode for a bistable phosphor is the conductive black backplate, a transparent metal film, then deposit on the inside surface of the faceplate before the phosphor is deposited. A width range of operating voltage on the electrode, about 100 to 200 volts, gives stable storage characteristic. So voltage below 100 volt will uniformly erase the target, and voltage about 200 volt will uniformly write the target. So the operating voltage is similar to the story like this one. We have a two crossover here before we get the stable condition, or to inject the electron to the phosphor screen is similar to the phosphor storage. So the voltage is around 100 to 200. Below 100 will be erase the target, and above 200 will uniformly write the target. So in this phosphor storage, the electrode voltage is already defined, is around 100 to 200 volts. Then you can find, and then you can find in the textbook about what is this phosphor characteristic and what is the persistence of the phosphor materials. Okay, then the next subchapter is about the CRO subsystem. We can see here we have at least four part of the CRO subsystem. The first one is vertical deflection system. Is we have the attenuator and also amplifier here, and then we have the horizontal deflection systems, including time-based generator and also synchronization circuits here. And then we have a CRT here, and also high volt and low voltage power supply. So this is the four important block in the CRO subsystems. The explanation of the CRO subsystem is similar to the conventional oscilloscope that we already discussed in previous week. Then this is the digital storage CRO. We have a preamplifier here, and then we have the analog to digital converter. We have a trigger circuit here to trigger the analog to digital converter and also the memory. And then we have the digital to analog converter, and then vertical amplifier to display in the CRO. And detailed block diagram of CRO you can see in figure 5.7. Okay. So the first one, we have the input. The input will coming to the input attenuator, and then will be amplified in the vertical amplifier. If the signal is coming to the sample and hold from the vertical amplifier, and then it will be trigger a circuit to the control logic here. And then after the signal is amplified in the vertical amplifier, is coming to the analog to digital converter, and then store the data in the memory. And also it will be controlled by the control logic here to the analog to digital converter and also the memory. And then the data out will coming to digital to analog block, digital to analog converter block, and then it will be amplified in the vertical deflection amplifier, and in similar process is coming from the control logic, because after the memory, after the vertical amplifier and then trigger circuit, we have the horizontal is from the digital, and then connect to the digital to analog converter, and then we go to horizontal deflection amplifier, and then we get the display in the CRT here. So the main differences between the digital storage CRO and also the analog storage CRO. In the digital storage CRO, we have the additional block. That is the analog to digital converter to store the data in the memory. And also, after we store the data in the memory, we have to restore the data to display the signal in the CRT. So we need a digital to analog converter here from the vertical deflection amplifier and also for the horizontal deflection amplifier. Okay, so this is the summary of the digital storage CRO. And then another important thing is the CRO probes. We can use these CRO probes in either we use in the digital storage CRO and also the analog digital CRO. So this is the equivalent circuit of the signal source and then a CRO. We have the ZS here. If the source impedance ZS is high, and then the small current drawn by the CRO input circuit might cause a volt drop across the source impedance itself. Therefore, the CRT display is not a faithful reproduction of the original signal amplitudes. Okay, at a high frequency, the shunt capacitance will play a role in the reduction of the signal amplitude and the phase shift. The cable being used to connect the signal to the CRO also acts as a combination between the R and C and can affect the signal reproduction on the CRO screens. Hence, the different type of the CRO probes are designed for the different application. So we can see here, if the source impedance CS is high, so the small current drawn by the CRO input from here, so may cause a voltage drop across the source impedance itself. Okay, so how to define, how to define the source impedance here in the CRO probe is very important, because a different type of the CRO probe have the different source impedance. So it will be affect the characteristic display in the screen. So you can see here, this is the additional, or the we have the parallel of the capacitance and also resistance here. The combination of the R and C and also affect the signal reproduction by the CRO screen. And in this case, we have to choose the appropriate CRO probe. So whether we will use the analog CRO or the digital CRO, and also the frequency of the CRO. So we will get the best display in the CRT screen if we use the appropriate CRO probes. So I think this is about the CRO probes. And then I have a subchapter that you have to make a self-study. The first one is about the frequency, period timer, and then also counter circuits, and then frequency measurements, period measurements, error in frequency or period measurements, and then the last is universal counters. So I think this is all of my presentations today. Thank you for your attention. Good morning. Assalamualaikum warahmatullahi wabarakatuh.